Hello everyone, this is another video on electrodynamics where we'll be discussing questions on from Griffith. Okay, we'll try to solve some Griffith questions. Okay, so here this question: find the field outside a uniformly charged solid sphere of radius r and total charge q. Okay, first draw the diagram for it. Just draw the diagram for it. Outside a uniformly charged solid sphere. This is a solid sphere. Okay, this is uniformly charged, right? Right. So field outside uniformly charged solid sphere radius r. The radius is r, charge is q. So we have to find the electric field. How to find this electric field here? Let's think about it a bit. Hmm, how to do it? So outside a outside this sphere, right? So for example, there is a point. There is this point here where we have to find the electric field. Okay. So what we have to do? We have to draw a Gaussian surface. Gaussian surface around it. The radius of that Gaussian surface will be small r. Okay, small r. So this is your Gaussian surface. Okay, radius is small r. So we have to find the electric field for this small radius of small r. Okay, we know what is that Gauss law. E dot ds integration E dot ds is equal to what? Q enclosed by epsilon naught. Alright, Q enclosed by epsilon naught. Okay. Mm, Here E is pointing radially outward. Right. And your D, see, E is radially outward, and your surface area ds is also kind of outward, right? So they're in the same direction. So I can say this is your eds cos 0, isn't it? Is equal to q enclosed by epsilon naught. So cos 0 is 1, so eds e I can take out ds, alright, ds. Okay, alright. Now the question in the question is given total charge is q, so I can write in place of q enclosed as small q divided by epsilon naught. Okay. What is the ds? What is the area of this Gaussian surface? Gaussian surface is e into 4 pi small r square is equal to q by epsilon naught. Okay. Yeah. So if I take 4 pi r square to that side, it will be e is equal to 1 by 4 pi epsilon naught q by r square r. Okay. So this is the result. Okay. Alright. So this is the formula for it. You must be thinking is the same formula. Yeah. But we calculated it the right way, isn't it? We did it proper way. So this is actually the field outside the sphere is exactly, if you see, exactly the same as it would have been if all the charge were concentrated at the center. At the center, so it would have been the same thing. E is equal to 1 by 4 pi epsilon naught q by r square. Okay. Okay, next question is go. Example 2.4. A long cylinder carries a charge density that is proportional to the distance from the axis. Charge density that is proportional to the distance from the axis. Rho proportional to s. S is your distance. So rho is equal to ks. Okay. Find the electric field inside the cylinder. Find the electric field inside the cylinder. So, for example, inside the cylinder is a long cylinder. This is the long cylinder. Okay, carries a charge density that is proportional to the distance. Rho is ks. Find the electric field inside the cylinder. So, I have to draw a Gaussian surface inside the cylinder. So, I will draw something like this, the Gaussian surface. Is that alright? Okay. So, this is the length. Suppose the length is L. Okay. Okay. This is the electric field. Alright. So again, if we use the Gauss law, E dot ds enclosed is equal to Q enclosed by epsilon naught. Okay. Now we need to find Q enclosed. Q enclosed is, we know, rho dV, isn't it? Rho dV. We have rho. Okay, we have rho. So rho dV will be Ks. Hmm. Uh, See here, actually AS is what distance. So AS, we generally take AS as what R, like distance is R. You can say K rho is equal to KR. So what is the volume element for cylindrical coordinate R dr d phi dz? Okay, R dr d phi dz. Okay, so here R dr will be what? SDS d phi dz. Is that alright? So I will take K out. So this will be your SDS. Sorry, this is s square ds, and the length is what, 0 to s, 0 to s d phi. D phi is a what, 0 to 2 pi, and dz is a 0 to l. Okay, length, this one. So this one will be k sq by 3 into 2 pi into l. So if I write it properly, it will be 2 by 3 pi q enclosed, 2 by 3 pi k l. It was what, kl sq, kl sq. So q enclosed is 2 by 3 pi kl sq, right? Hmm? So mm, now see, it's like this. Electric field is now along this direction. Area vector is also along this direction here. Okay. So if I see E dot dA ds, okay, um, ds, yeah, ds is equal to E dA ds. Here, okay, no problem. So E ds. Here ds is how much? Can you tell me? This is 2 pi r and length is L. Sorry, length is S here, right? Length is S. So this one will be 2 pi. Mm, length is L. Length is L, but here this one is 2 pi S, right? Yeah. Here I'm getting confused. Rho is equal to Ks, na? That's why R is taking, S is replacing R. So 2 pi S. So 2 pi S into L. Okay, so this is your 2 pi e ESL. Alright. So this is your E dot ds. We know E dot ds is equal to q enclosed by epsilon naught. So 2 pi ESL is equal to 2 by 3 pi KL SQ divided by epsilon naught. Okay, pi got cancelled, 2 got cancelled. So S will be S square, LL got cancelled. So E is equal to how much? E is equal to K SQ S square by epsilon. Okay, and if you give a vector sign, this will be S vector because we were giving R vector. So everything is being replaced by S here in this question. So E is equal to K square by 3 epsilon naught S cap. So this is how we used cylindrical coordinates. Okay, cylindrical coordinates is what? RdR, volume element is RdR d phi dz. This is the radius. This is 0 to 2 pi, 0 to length. Is that alright? Yes. Hmm. Solving these questions will really give you a very good conceptual funda. If you see. This question is done. Next question, 2.5. An infinite plane carries a uniform surface charge sigma. Okay, find its electric field. Just one line. Okay, infinite plane is there. Carries a uniform surface charge sigma. Infinite plane. Electric field will be something like this, isn't it? So what I have to do is I have to take an element of this. I always take elements. Okay. So see here. Um, Either ds is equal to again enclosed by epsilon naught. EDS. How do we find EDS here? So E is pointing away from the surface. Here also pointing away. So if you see E minus minus E, 2. So for this surface is there, for the upper surface, E into A. For lower surface also there, plus E into A. Yeah, that's alright. Let's go to Q enclosed by epsilon naught. What I did was this related to like the upper surface is also going away, lower surface is also going away. Upper surface also area vector is away, lower surface area vector is away. So you can see these are in same direction. So this is area cos theta, that is EA. EA cos theta, that is EA. So EA plus EA I'm writing. This is 2EA is equal to Q enclosed by epsilon naught. Okay. We know Q is equal to what for a surface charge? We know surface charge density sigma is equal to Q by A. Q is equal to A sigma by epsilon naught. Sorry. A got cancelled. So E is equal to how much? Sigma by 2 epsilon naught. Sigma by 2 epsilon naught. And it will be n cap. N cap is this one. Unit vector along a perpendicular to the plane. Okay, pointing away from the surface. Is that alright? Yes, see once. This question is done. Okay. An infinite plane carries a uniform surface charge sigma. Find its electric field. We just find it sigma by 2 epsilon naught. Okay, I'm giving you 2 minutes. Please see through this. If you have any doubt, please let me know. Let's move to the next question. Problem number 2.15. A thick spherical cell carries charge density rho is equal to k by r square. And find the electric field in three regions. Okay, this one. Please try once. Try this question. Okay, see. Spherical cell like this. So, what's that? This is our R distance, this is our A, this is our B, this middle part is our R, isn't it? So, find the electric field in the three regions. First region R is less than A less than R, R greater than B. Plot E as a function of R for the case B is equal to 2A. So, first tell me. Okay. For r less than a, if you see, for example, the inside one, a. So for r less than a, can you tell me what is the charge enclosed? What is the charge enclosed? Because see, the charge density k by r square, it's actually between what? A less than r less than b. So the charge density is actually between a less than means it's actually between this region, isn't it? A, this is b. So the charge density is actually between this region. There is no charge density inside this sphere. There is no charge because it's given in the question. We have to find it out. Okay, you'll be thinking how here is zero because here charge density is given between A to B, between these two. Okay, so charge density is zero where if R is less than A, isn't it? It's not given. We have to figure it out. So if charge density is zero, then what? Q enclosed will be zero, isn't it? Because Q by V is your charge density, right? Charge by volume, volume charge density. So Q will be what? Q will be your zero. If Q is zero, so E dot ds 0. Q enclosed by epsilon, so E is 0. So electric field in the R less than A region is 0. Is that correct? Okay. Now what? Now we have to find what? A less than R less than B. Now for A less than R less than B, we have to find out electric field. Right? How to do it? We know the charge density in this region. Charge density rho is equal to K by R square, right? K by R square, na? Yeah, very good. K by R square. So we know Gauss law E dot ds Q enclosed by epsilon naught. Q enclosed, we can say Q enclosed is what? Rho dv integration. Okay, volume integration of rho dv. Rho is K by R square. This is spherical polar coordinates. So R square sine theta d phi. Is that right? D theta d phi? No? Yeah. I'm missing some. Yeah, dr. R square sine theta d phi dr. Integration. Triple integration it will be. K will come out. Sine theta d theta 0 to pi d phi 0 to 2 pi dr. What will be the limit of dr? Can you tell me? What should be the limit of dr? Because see here, the as I said in the previous part of this question, there is no charge in this inner sphere. The sphere with radius A, there is no charge. So the charge density is actually starting from here, from this A point. Okay, from A to B only. But we have to find electric field from where to where? A to R here, isn't it? At a point like at a distance R. That means A to R. Because A to R there is, this is A. A to R. There is electric field in A to A R only here. Up to R. A to R. Did you get it? So K sine theta d theta 0. This one will give me 2. And this one will give me 2 pi. And this is your R minus A. Answer is 4 pi K R minus A. Is that alright? 4 pi K R minus A. This is what? This is your Q enclosed. Okay. Now I'll put it here. So E dot ds is equal to Q enclosed by epsilon naught. Q enclosed is 4 pi K R minus A epsilon naught. So E dot ds will be up to which point again? Tell me. See, again, Gaussian surface is up to R, small r. So E into 4 pi R square is equal to 4 pi K r minus a by epsilon naught. So E is equal to k by epsilon naught r square r minus, and the vector sign will be given like if I write, let's write it a bit properly. K by epsilon naught r minus a by r square r. Is that all right? Is that all right? Okay. See, it's not that hard. It's just a bit of conceptual. We have to know the limits, which limit to put, what to do. What is the next option in this question? These two are over. Next is R is greater than B. So we have to find for R is greater than B. So let's find for R greater than B. How to find R greater than B? C. Again, same diagram. There is no charge inside. There is only charge in this region of this spherical cell. R is greater than B. That means R is here now. So tell me, the electric field at this point will be because of what? Will be because of the charge density that is only in this spherical part, this A to B, isn't it? So electric field will only be because of this part, A to B part. So according to that, we'll calculate. Okay. So again, E dot ds is equal to what? 1 by epsilon naught rho dv, 1 by epsilon naught k by r square into r square dr sine theta d theta d phi. Here the limit matters. Limit is A to B. Why? Because only between A to B the charge density is there, and because of that charge density I will get electric field at this point. Okay, not A to R. You must be thinking A to R. No. Why A to R? Why? Because there is no charge density between this B to R. So why will we even consider it? We will only consider A to B. So 1 by this cancelled. K comes out K by epsilon naught. This is again dr A to B sin theta d theta 0 to pi d phi is 0 to 2 pi. So k by epsilon naught b minus a into 2 into 2 pi. This is 4 pi k by epsilon naught b minus a. But this is only your EDS. So EDS E into 4 pi r square is equal to 4 pi k b minus a epsilon. Now you can ask me why this is small r square. Because the Gaussian surface should also always be considered for area. Gaussian surface R, right? Yeah. 4 pi cancelled out. So E is equal to K by R, K by epsilon naught, B minus A by R square. Is that all right? And this one again. Okay. Yeah. So this is a related field. Next question. Problem number 2.17. An electric plane slab of thickness 2D carries a uniform volume charge density. Okay. Find the electric field as a function of y, where y is equal to 0 is at the center. Plot E versus y, calling E positive when it points in the y direction, negative when it points in the y direction. Again, read the question. Read the question again. Infinite plane slab. So, there is an infinite plane slab. Okay, thickness is 2D. Thickness is this is like 2D. Okay. Carries a uniform charge density rho. Find the electric field as a function of y, electric field as a function of y, where y is equal to 0 at the center. Hmm. Plot E versus Y, calling E positive when it points in the positive y direction, negative when it points in the negative y direction. Right? So this is a thing to think about. This is a question to think about a bit, and not really think about it a bit actually. Uniform volume charge density here. This is the slab. This is infinite tensile thickness to D. Electric field ADS as usual is equal to rho dV by epsilon naught, isn't it? Rho dV will be how much? Otherwise, we can simply write as Q enclosed by epsilon naught. Okay, Q enclosed by epsilon naught. Now then, what is Q enclosed? See, um, thickness is 2D. It's not an uh, volume charge. Okay, charge will be what? How much Q and rho into volume, right? Volume is area into length. That is this is it's function of y, where y is equal to 0 is at the center. So it's better to y is equal to 0 is at the center. That means the x-axis is along the is like the center. So going to be should be another term which will give me volume, right? Area into something is volume, area into distance. So what we think is here even in the point equals well, even the, so calling E positive in the positive y direction, negative in the y direction. So what can I do here is I can multiply y, which is actually the distance. So area into distance we know is actually volume here. Okay, so I put it here. Rho a y by epsilon naught. Okay, so E dot ds is how much? E into a. Ds is a. So a got cancelled out. E is equal to rho of y by epsilon naught. Okay, rho y by epsilon naught y. Rho y by epsilon naught y. Why y cap? Because y. This is a function of y and it's in the direction of y direction. Because here E positive when it points in the plus y, points in the zero. Clearly it's written that E at least points in the y direction. Okay. So this is the answer, yeah. Hmm. See here, this one is the one we got here is actually y less than d. D as we have seen here, 2D is the thickness. So D is the half of the thickness. Alright. This is Y less than D. Y greater than D would be simply I will put in place of Y just D. Q dy cap by epsilon naught. Right? Yeah. Okay. Got it. So next question. Let's move to the next question. Problem 2.25. Using equation 2.2, the potential at point Z above center of the charge distribution in 2.34a, this one, and in each case, the camp the compute in each case compute E is equal to minus del V. Okay, compare your answers with this one. Suppose that we change the right hand charges, then what is the potential of P if we change the sign? Agree? Yeah. Uh, Suppose that we change the right hand charge. Okay. Okay, so how to solve this one? Think about it first. Think about it. Okay, see. Potential at distance Z. First one we will draw. Yeah. So this is the diagram. Maybe thinking why I'm taking so. Yeah, I have to think about it first, then only I can solve it. Because the potential is actually only for person not 2q by so square plus d square for like for zones. So v is equal to 1 by 4 pi epsilon naught 2q by total z square plus d square by 4, right? So now, what is the question next is what does this suggest? Compare an answer to problem to convert. So this is what is the question? Find the potential. No potential to be found. This question is a bit weird. Okay, next is this one is for one. Which one? First one. Okay. Why this one is this? See if you see. This is your d by two. This is the z direction. This is your z square plus d square by 4 root over. We need this distance only. D square by plus d square by 4. Like we need what? We need cos theta, sin theta. Alright, those things. So 1 by 4 pi epsilon naught 2 q by common x square. Okay. 2 q by root over of z square plus d square by 4. Alright. Yeah, yeah. Next question is that this one, the middle one, uniform line charge density. You do this one, line charge density. So here you have to find potential again. 1 by 4 pi epsilon naught minus L12. Why minus L12? It's urging people to do. So it's urging you to like what? Take the limit from minus L to L. Why? Because it's a length to L, isn't it? So minus L to L. So take it minus L to L, and your this one is a lambda px divided by z square plus x square. Right, again same thing, z square plus x square. Why? Because I'm sorry, this is distance. Okay, and this is z, this is x, so z square plus x square. Alright, so this is your integration. If you do the integration, so the integration will be lambda by 4 pi epsilon naught ln x plus root over of x square plus z square. This is minus L to L. Okay, so my lambda by 4 pi epsilon naught ln y divided, because they are subtracted, so it's better to divide them. Right, this is the answer for it. This is the answer for this question. Okay. Next is your this disk kind of thing here, right? This radius is r, and I guess representing sigma. This is z. This is p, which way where we have to find the potential. Okay. So see here, what is the limit 0 to 1? Because it's the radius we have rotating radius. So potential for this one will be potential V is equal to 1 by 4 pi epsilon naught 0 to R. 0 to R. What is it? Here charge density sigma. Sigma into length. Okay, so sigma into 2 pi R because there will be no area. Sigma into 2 pi R dr divided by R square plus Z square root over 8 R square plus Z square root over. Okay, so if you see 2 pi goes out 1 by 2 epsilon naught sigma 0 to 1 R by 2 R square plus Z square dr. Okay, so if I multiply to divide 2 sigma by 4 pi epsilon naught, this integration will be its derivative is here. So for example, there is an integration f dash x divided by root over of f of x dx. That will be what? 2 root over of f of x plus c. So here I can write 2 root over of z square plus z square 2 root over of r square plus z square and z square and the 0 to 1. Sigma by 2 epsilon the 2 will be cancelled out too. Sigma by 2 epsilon naught root over of r square plus z square root over. Right, is that right? Oh, so minus 0 will also be put to z. Okay, alright. This is your potential. So potential for this spherical one. Like the disk one of the sphericals, okay? The disk one. Is that right? Okay. Yeah, this is the one for these two questions. No, this is different. Yeah, sure. This is different. I'll do this tomorrow, okay? So that'll be it for today. And yeah, thank you very much for listening. Thank you.